Imagine trying to create like a really intricate 3D scene on your computer, like really detailed and fully optimized.
Yeah.
That could take minutes or even hours with the current tech.
Oh, absolutely. I mean, that's just the reality of 3D creation pipelines right now.
Yeah.
You often have to generate tons of different perspectives,
Right.
and then you have to use these really complex optimization techniques to stitch it all together into a final 3D model. And it's possible to get great results that way, but it just takes so much time and processing power.
Yeah, it's a real bottleneck. So what if we could speed that whole process up?
Right.
Like make it almost instantaneous?
Yeah.
Well, that's what we're diving into today.
Okay.
There's this new model called Bolt3D.
Interesting.
And get this, it can create a 3D scene in about 6
Oh,
seconds
6 seconds.
on a single GPU.
That's incredible. I mean, that
Yeah.
kind of speed, it just completely changes the game for 3D.
Yeah.
You got to have like real-time interactive visualization and editing.
Right.
Or you could generate these huge libraries of 3D content for all sorts of applications. It's not just a small improvement. It's like a 300 times speed increase.
Yeah.
It could completely change how we create 3D content. Like, imagine a designer being able to change and play with a complex scene in real time.
Yeah.
That used to be something that would take a whole team.
Yeah, tons of computing power.
Right.
So our mission today is to look at this paper. It's called Bolt3D, Generating 3D Scenes in Seconds.
Okay.
And we want to understand exactly how this model achieves that kind of speed,
Right.
what it can actually do, and what its limitations are. So let's start with the basics. Like, why has creating detailed 3D scenes been so difficult in the past? What are like the fundamental challenges?
Well, I think one of the biggest challenges is just how you represent and structure 3D data.
Right.
It's unbounded. It can be infinitely complex.
Right. You can't just treat it like a 2D image.
Exactly. You need a completely different way of thinking about the problem. And then, on top of that, we just don't have as much of 3D data to work with.
Oh, so it's like the data set problem all over again.
Exactly. Like when you compare it to the huge amount of 2D image data that's out there,
Right.
the amount of high-quality 3D scene data is pretty small.
Yeah.
So that makes it much harder to train really robust 3D generative models. And because of all of that, a lot of the early 3D generative models were very limited.
Okay.
They could maybe create like individual objects that looked pretty synthetic, or they could only generate partial views of a scene,
Yeah.
not the kind of full immersive environments that we're looking for now.
And you mentioned before some of the newer techniques that use multi-view or video diffusion.
Right.
They're already generating multiple perspectives, right? So why are they still so slow?
Yeah, that's a good question. So those methods, they typically start by generating like a ton of synthetic views from the initial input images,
Okay.
like hundreds of views. And they use a diffusion model to do that.
Right.
But then they have to go through this whole separate optimization process to reconstruct the 3D scene from all those views. And that's what takes so long. It's this computationally intensive puzzle-solving step.
Right.
It can take minutes or even hours to stitch it all together.
So it's generating all those puzzle pieces and then trying to like painstakingly fit them all together.
Yeah, exactly.
Okay. But you described Bolt3D as like a fast feed-forward generation system.
Yeah.
So how does it manage to bypass all of that?
Okay, so Bolt3D is what's called a latent diffusion model,
Okay.
and it's designed to directly generate a 3D scene representation in a single pass.
Okay.
So it doesn't need that separate optimization step. It essentially skips the puzzle assembly altogether.
It just goes straight to the solution.
Yeah, pretty much.
Yeah.
And one of the key innovations here is that Bolt3D builds on all of the progress that's been made with 2D diffusion models.
Right.
It uses these really powerful and scalable 2D network architectures to create a coherent 3D representation.
So it's adapting the 2D advancements for 3D.
Exactly.
Yeah.
And the difference in speed is just dramatic.
Right. We're talking less than 7 seconds versus minutes or even hours.
Right. The paper says that Bolt3D can reduce the inference cost by up to 300 times compared to those multi-view methods.
That's a huge improvement.
It's massive.
Yeah.
So, okay, so we know it's fast, we know it's direct,
Yeah.
but how does it actually represent these 3D scenes?
Right.
You mentioned 3D Gaussians stored in 2D grids.
Yeah, that sounds complicated.
Yeah, it is a little bit. So imagine each 3D Gaussian as like a tiny blurry blob in 3D space.
Okay.
And each blob has its own properties, like its color, its position, its opacity, and its shape.
So it's like a point cloud, but each point is a little more complex.
Yeah, that's a good way to think about it.
Mm.
And Bolt3D stores all of these 3D Gaussians, in multiple 2D grids.
Okay.
They call these splatter images. It's like taking snapshots of the scene from different angles and projecting those blobs onto each snapshot.
I see. So you've got multiple 2D images, but they're actually holding all the data for a 3D scene.
Exactly.
That's clever.
Yeah, and here's the really interesting part. Bolt3D actually generates more splatter images than the number of input views it receives.
More?
Yeah, more.
So it's creating information for parts of the scene that it hasn't even seen. It's
Geomet-
like it's hallucinating.
Yeah, kind of. It's using a diffusion model to fill in the gaps in the 3D scene based on what it has seen.
Okay, so it's not just reconstructing, it's actually predicting what should be there. So the paper describes this as a two-part generation process.
Right.
Can you break down those two steps?
Yeah. So the first step is what they call denoising. And basically, Bolt3D starts with a really noisy representation of the scene,
Okay.
and then it uses a latent diffusion model to gradually refine it, removing the noise and revealing the underlying structure.
So it starts with a bunch of digital static and then kind of sculpts it into a real scene.
Exactly. And then the second step is called regression.
Okay.
And this is where another neural network comes in. It's called the Gaussian head network.
Right.
And it takes all the information from the denoising step, and it predicts the rest of the properties for each Gaussian.
So the denoising step establishes the structure, and then the regression step fills in the details.
Right. Things like the opacity and the shape of each blob.
Okay.
And it also refines the color information.
So what kind of input does Bolt3D need to get started?
So it needs a set of posed input images.
Posed.
Yeah. So that means that each image has information about where the camera was when the picture was taken,
Okay.
like its position and orientation.
Got it.
And it also needs a set of target camera poses,
Okay.
which are basically the viewpoints that it needs to generate the 3D scene from.
So it knows where the original images were taken from, and then you tell it where you want to view the scene from.
Exactly.
And then it generates the 3D scene from those new perspectives.
Right. And it outputs both the appearance of the scene, like the colors of each pixel,
Right.
and the 3D coordinates of each point in the scene from all of those camera views.
Okay. So the paper also mentions this thing called a geometry VAE.
Yes.
What is that?
So that stands for Geometry Variational Autoencoder.
Okay.
And it's really important for getting the 3D geometry right. It's different from a regular image VAE.
How so?
Well, image VAEs, they're trained on color and texture information.
Right.
But the geometry VAE is trained specifically on 3D geometry data.
Okay. So it's specialized.
Yeah. And that's important because image VAEs, even if you try to scale them up, they don't really work well with unbounded 3D geometry.
It's the wrong tool for the job.
Exactly. Yeah. So the geometry VAE has a similar architecture to image VAEs,
Okay.
but it's optimized for encoding and decoding 3D geometry information.
Got it.
And that allows Bolt3D to predict the 3D structure of the scene much more accurately.
You were talking earlier about the scarcity of 3D training data.
Right.
So how did they get enough data to train this geometry VAE and the whole diffusion model?
Yeah, that's a good point. They had to get creative. So what they did was they used a bunch of existing multi-view image data sets,
Okay.
like CO3D, MVIMEG, Real Estate 10K, and DL3DV7K.
Those are all image data sets, right?
Yeah. But they used a technique called structure from motion to reconstruct 3D models from those images.
So they turned 2D data into 3D data.
Yeah, basically. And that gave them a large enough data set to train the geometry VAE and the diffusion model.
That's really clever.
Yeah, they also used some synthetic object data sets to help with the training.
Okay.
So things like Objaverse,
Right.
and then some internal data sets that they had.
So we've talked about the denoising step. We've talked about the geometry VAE.
Right.
But what about that Gaussian head network that you mentioned? What exactly does it do?
So the Gaussian head network takes all of the output from the denoising network.
Yeah, okay.
So that's the high-resolution images, the 3D geometry maps, and the camera poses.
Right.
And its job is to predict the remaining properties of those 3D Gaussians.
Like their opacity and their shape.
Yeah, exactly.
Okay.
And it also refines the color information.
So it's like adding the finishing touches that make the 3D scene look real.
Right. And it's trained using rendering losses.
Rendering losses.
Yeah, so basically the model is comparing what it generates to the actual ground truth views.
Okay.
And that helps it learn to create 3D scenes that can be rendered into high-quality images from any viewpoint.
So how does Bolt3D stack up against other methods? Like, how good is it really?
Well, the paper has a whole section on evaluation.
Okay.
And they compared Bolt3D to a bunch of different methods.
Okay.
So first, they compared it to these feed-forward 3D regression methods,
Okay.
like Flash 3D and DepSplat.
Okay.
And Bolt3D consistently outperformed them, especially in situations where there weren't many input views or where the views were kind of limited.
Right. So if you only have a few glimpses of the scene, Bolt3D is better at filling in the gaps.
Yeah, exactly. It's that generative approach. It's able to model uncertainty and create more plausible content.
That makes sense. What about other feed-forward 3D generative methods?
Well, they compared Bolt3D to latent splat,
Okay.
which is another method that learns a latent geometry representation. But Bolt3D still did better. It created more realistic and detailed 3D scenes.
And it's also more versatile, right? Like it can handle different types of scenes and different numbers of input images.
Yeah, exactly. So then the big question is, how does it compare to those really high-quality optimization-based methods,
Right.
like CAT3D?
Right. Those are the ones that are really slow.
Yeah, exactly. And what they found was that Bolt3D is actually competitive with those methods in terms of visual quality.
Really?
Yeah, there might be a tiny drop in some of the quantitative metrics,
Okay.
but Bolt3D is 300 times faster.
Wow.
So it's a trade-off, but it's a pretty amazing trade-off.
Yeah, 300 times faster for a slight dip in quality.
Right. And qualitatively, the paper shows that Bolt3D creates really high-quality reconstructions for a variety of scenes.
Okay.
And sometimes it even generates sharper details than the optimization-based methods.
So it might actually be better in some cases.
Yeah, potentially.
That's really interesting. You mentioned earlier how important that geometry VAE is. Can you explain again why it needs to be trained specifically on geometry?
Yeah, so the paper actually shows that pre-trained image autoencoders just don't work well for unbounded 3D geometry.
So you can't just take a pre-trained image VAE and use it for 3D.
Nope.
It just doesn't understand the structure.
Exactly. The geometry VAE, because it's trained specifically on geometry data, it's much more accurate at encoding and decoding the 3D information.
I see.
And that's probably why a lot of the earlier latent diffusion models have focused on objects rather than full scenes.
Right, because they didn't have that specialized geometry understanding.
Exactly.
So are there any limitations to Bolt3D?
Yeah, there are a few things that the paper mentions. So it can have some trouble with really thin structures,
Okay.
like things that are less than 8 pixels wide.
Right.
And that's probably because of the downsampling that happens in the geometry VAE.
Right. It loses some of that fine detail.
Yeah. And it can also struggle with scenes that have a lot of transparent surfaces or really reflective surfaces, because those are hard to reconstruct accurately in the first place.
Makes sense.
And finally, the model can be a little sensitive to how the target cameras are defined,
Okay.
like the up vector and the scale of the scene.
Right.
So there's definitely room for improvement.
Sure. But overall, it sounds like a pretty big step forward.
Oh, yeah, absolutely. I mean, being able to generate detailed 3D scenes in seconds is a huge breakthrough.
Okay, so just to recap, Bolt3D is a new model that can generate detailed 3D scenes in just seconds.
Right.
It's much faster than older methods. It uses this fast feed-forward latent diffusion process. It represents scenes using these collections of 3D Gaussians stored in 2D images.
Right.
And it has this specialized geometry VAE that helps it understand 3D structure.
Yeah.
It outperforms other feed-forward methods, and it's even competitive with those much slower optimization-based approaches.
Right.
So it's not perfect yet,
Yeah.
but it has the potential to really change how we work with 3D.
Yeah, absolutely.
And just a reminder, this whole deep dive was based on the research paper Bolt3D, generating 3D scenes in seconds.
Right.
So we encourage you to go check out the paper and also the project website. They have some really cool interactive demos that show off what Bolt3D can do.
Yeah.
So the big question is, what are we going to do with this technology? Like, what are the new applications? What are the creative possibilities?
That's what I'm really excited about. I mean, think about it. We can now generate these detailed 3D environments almost instantly.
Right.
So how is that going to change things like gaming
Yeah.
or VR
Right.
or architecture
Yeah.
or even scientific modeling?
Or just how we perceive and interact with information.
Yeah, it could change everything. It's a whole new world of possibilities.
It's really exciting to think about.
It is.
So that's it for this deep dive. Thanks for listening.
Thanks for having me.
See you next time.
See ya.